So previously, you would have drawn straight line graphs, y equals mx plus b, quadratics, y equals ax squared plus bx plus c, and maybe even cubics. What we'll be looking at today is drawing graphs of even higher degrees. For example, in this question, we have x indice 5 and x indice 4. So what we'll do is break this down into 3 steps. The first step is the leading term test, where we'll identify the end behavior of the function. The second step will be to identify the maximum number of turning points and identify the zeros, meaning the values of x where the function is equal to 0 and passes through the x-axis. The third and final step will be to plot additional points by making a table and drawing the graph. So in the previous lesson, you should have looked at monomial functions. Now, what is a monomial, or what does it mean? Monomial just means one term. Now on the right, we have monomial functions of x to an even degree. And so you might have noticed that all of them are in the shape of the letter U, which we call a parabola. On the left, we have monomial functions of x to an odd degree. So x indice 1, x indice 3, x indice 5, x indice 7, and so on. You might have noticed that with the exception of x indice 1, which is a straight line graph, functions of x with an odd degree are similar in shape to the cubic graph. Check your understanding. Which of the following is not a possible function of the graph displayed above? fx equals x indice 10, fx equals x indice 11, or fx equals x indice 12. Pause the video and play when you're ready to answer. As we have a U-shaped graph, known as a parabola, we know that we have a monomial function of x to an even degree, or an even indice. So x indice 10 is possible, and x indice 12 is possible. X indice 11 is an odd degree, and so we know this will be a cubic shaped graph. Which of the following is a possible function for the graph displayed above? fx equals x indice 1, fx equals x indice 8, or fx equals x indice 13. Again, pause the video and play when you're ready to answer. As we have a cubic shaped graph, we know that we must have x to an odd indice, and so x indice 8 is not possible. Now we have fx equals x indice 1 and fx equals x indice 13, but we know that x indice 1 will be, yes, a straight line, and so the answer will be fx equals x indice 13. So again, in the previous lesson, you should have covered monomials. So for example, we have fx equals x squared, fx equals 2/3 x cubed, fx equals minus 9, fx equals minus 4. Now when we put monomials together, we form what are known as polynomials. How many monomials do we need to make a polynomial? Well, it's a bit like saying, how many bricks do we need to make a wall? The answer is, as many as you like. So if you think of monomials as bricks, and the polynomials as a wall, where we put one or more type of brick together, then we can define a monomial as a wall with one type of brick, a binomial as a wall with 2 different types of brick, and a trinomial as a wall with 3 different types of bricks. Somebody said to you, describe the wall. You wouldn't say, there's 1 brown brick, plus 1 brown brick, plus 1 grey brick, plus 1 orange brick, plus 1 grey brick, plus 1 brown brick, plus 1 orange brick, plus 1 brown brick, plus 1 grey brick, plus 1 brown brick. Instead, you'd collect the like terms and you'd say there are 5 brown bricks, 3 grey bricks, and 2 orange bricks. Similarly, when describing polynomials, we make sure we simplify and collect the like terms. So in this example, we'd say we have 4x indice 5 minus 2x and plus 4. This polynomial is a trinomial because there are 3 distinct terms. So, f of x equals 7x squared is a monomial function as it contains one distinct term. F of x equals 4x to the indice of negative 2 is one term, however, we don't allow negative indices in polynomials. Just think of it like putting a hole in the wall, as when you plot this graph, there will be a hole in the graph. Now, f of x equals 7x squared plus 13x is a binomial function as it contains 2 distinct terms. It can't be simplified further. Now, if you look at f of x equals 2x cubed plus 6x cubed, this can be simplified to 8x cubed, which is one distinct term, and so we classify this as a monomial function. Similarly, f of x equals x indice 7 plus 2x indice 7 plus 3x plus 4x can be simplified to 3x indice 7 plus 7x. And so, although it contains 4 terms, when you simplify it, it only contains 2 distinct terms. And so this is a binomial function. Finally, to give an example of a trinomial function, f of x equals 2x indice 3 plus x indice 8 minus 5x squared. Degree and leading coefficient. So, when we want to find the degree and leading coefficient, we follow 3 simple steps. Let's look at some examples. So we have, in the first example, f of x equals 9x plus 16. So we want to find the leading term, so step 1, we identify the term of x with the largest indice. In this example, we only have one term with x, which is 9x, so our leading term is 9x. The degree will be the value of the indice in this term, which is 1. And step 3, the value of the coefficient in the term is 9. Let's look at example 2. So again, we follow the steps. So step 1, identify the term of x with the largest indice, that's minus 3x squared. The degree will be 2, and the leading coefficient will be minus 3. Now, let's look at the third example. The leading term is 2x cubed. How did we get this? Well, we have minus x, we have 2x, and we have minus x. Don't forget, as these terms are in brackets, we need to multiply them in order to find the leading term. So by multiplying these terms, we get 2x cubed. The degree will be 3, and the leading coefficient will be 2. Similarly, for the last example, we need to multiply 2x squared, x, and minus 5x. By multiplying these, we get minus 10x indice 4, the degree is 4, and the leading coefficient is minus 10. Activity. Mr. Muhammad needs your help to mark his students' homework by writing the correct answers for the questions answered incorrectly. Pause the video and play when you're ready for the answers. Behavior. On the right, we have examples of polynomial functions with even degrees, and on the left, we have examples of polynomial functions with odd degrees. We're interested in how degree affects the end behavior of a graph. The end behavior is simply how the graph behaves towards its ends. So, first, let's look at examples of polynomial functions with odd degrees and how that affects the end behavior. So when the leading coefficient is positive, and as x becomes larger, the function of x becomes larger. As x tends towards negative infinity, then the function of x will go down towards negative infinity. If my leading coefficient is negative of an odd degree, for example, the function of x equals negative x indices 3, then as my x values become larger towards infinity, my function of x will go down. And as my x values tend towards negative infinity, my function will go up towards infinity. Let's look at examples of polynomial functions with even degrees. If my leading coefficient is positive, then as x tends towards infinity, the function goes up towards infinity. And also, if x tends towards negative infinity, my function will go up towards infinity. However, if my leading coefficient is negative, as x tends towards negative infinity, the function will go down towards negative infinity. And as x tends towards negative infinity, the function of x will go down towards negative infinity. As you can see, in the examples of polynomial functions with odd degrees, the end behaviors will be opposite. So only one side will go up and one side will go down. Whereas with examples of polynomial functions with even degrees, both sides will either rise or both sides will go down. So let's look at some transformations. So if we have a monomial function with a negative coefficient, for example, f of x equals x squared becomes f of x equals negative x squared, the graph will flip over. Similarly, with f of x equals x indices 3, if that becomes minus x indices 3, the graph will flip over. Scaling. If our coefficient of the monomial is larger than 1, it means that our graph will stretch away from the x-axis. If it's between 0 and 1, it means that the graph will become more and more flat. Vertical shift. For example, if we have f of x equals x indices 8, if we add 3, the graph will rise upwards. If we put minus 5, it will go down. Horizontal shift. In the case, for example, f of x equals x indices 10, if we have f of x equals x minus 6 indices 10, the graph will move to the right. And if we have f of x equals x plus 8 indices 10, the graph will move to the left. Which of the following is a possible function for the red line in the figure above? Pause the video and play when you're ready for the answer. Which of the following is a possible function for the blue line in the figure above? Pause the video and play when you're ready for the answer. Which of the following is a possible function for the green line in the figure above? Pause the video and play when you're ready for the answer. Activity. Pause the video now and play when you're ready for the answers. Turning points. So what are turning points? Turning points are the points at which the function changes from increasing to decreasing or decreasing to increasing. The rule is a function of degree n can have a maximum of n-1 turning points, and the degree must always be larger than the number of turning points. So for example, this graph has 4 turning points, and so it must be degree 5 or more. It cannot be degree 4 as we have 4 turning points, and the degree must always be larger than the number of turning points. So this graph here has 2 turning points, so the minimum degree must be 3. Pause the video and complete the rest of the answers for yourself. Play when you're ready for the answers. Which 2 of the following statements are true? Pause the video and play when you're ready for the answer. Zeros of a polynomial. Zeros of a polynomial are the points at which f of x equals 0, identified by the points where the function intercepts the x-axis. For some polynomials, you could identify the zeros by factorizing. For example, f of x equals x squared plus 2x minus 8. We let f of x equals 0, factorize, and then we find that x equals minus 4 or x equals 2. The degree of a polynomial is also the maximum number of zeros it could have. So for example, in f of x equals 13x indices 7 plus 5x indices 6 minus 8x, this would have a maximum of 7 zeros. Zeros of a polynomial function in quadratic form. This is when we have a trinomial where the b term has an indice which is half of the indice of the leading term, otherwise known as the a term. So for example, if we have ax indice 6, we would have bx indice 3. If we had ax indice 10, we would have bx indice 5, and so on. So on the left, I have my question, on the right, your question. So please follow the steps I do in my question on the left, and do the same in your question on the right. So first I'll let f of x equal 0. Then I want to change my a term so I have a similar indice as my b term. So my b term is minus 3x indice 2. So I'll change my x indice 4 to x indice 2 squared. Now I'll let u equal x squared. So I'll have 0 equals u squared minus 3u minus 4. And then we'll factorize. So I'll have 0 equals u plus 1 multiplied by u minus 4. Now I'll substitute back into this my x squared that I had originally. So now 0 equals, in brackets, x squared plus 1 and multiplied by x squared minus 4. This can be further factorized, and then I find my solutions. So my graph will look like this. I have x equals minus 2, and I have another 0 at x equals 2. Pause the video and play when you're ready for the answers. trinomial functions with descending indices. So in this case, as each indice of x is larger than the one that follows it, we let f of x equal to 0, and then we factorize out x to the n minus 2, okay, which is going to be the indice in our c term. We should be then left with a quadratic, which we can then factorize. So again, let's do an example. So again, f of x equals 0. My c term has x indice 2, which is the common factor of all of my terms. I can then factorize this out, leaving me with x squared and in brackets minus x squared plus x plus 2. I then have a common factor of minus 1 inside the bracket, so I can take this to the outside. I then factorize my quadratic, and then find my solutions. Pause the video and play when you're ready for the solutions. Repeated zeros. So, when a zero occurs more than once as a solution to a function, it's referred to as a repeated zero. So for example, in this function, when I factorize this down, I get x plus 3 multiplied by x plus 3 multiplied by x plus 3 multiplied by x plus 3 equals 0. In other words, I have x equals minus 3 as a solution 4 times, okay? Or we say multiplicity form. In this graph on the right hand side, which is f of x of 2x indice 5 minus 8x indice 4 plus 8x indice 3, when we factorize this down, we get 0 equals 2x indice 3 multiplied by x minus 2 squared. So we'd have x equals 0 as a solution 3 times, and x equals 2 as a solution twice. So let's now try and plot this graph. So read the question and then play when you're ready. So the first thing we'll do is carry out the leading term test to determine the end behavior. So we can see our leading term is 2x indice 5, the degree is 5, and so we also have a leading coefficient of 2. Therefore, as x tends towards infinity, the f of x will tend towards infinity, and as x tends towards negative infinity, f of x will go down towards negative infinity. We then determine the zeros and how many turning points we should have. And then, using a table, we plot additional points and then draw the graph.